Hello, everybody, again. So, thank you for joining uh, for the last day of the first DataFest Yerevan. Our first speaker for today is Harutyunyan from University of Southern California. He's actually our only speaker who is joining us from the other side of the ocean, and that, of course, brings with itself the discomfort of the time zone. So, thank you, Hrayr, for joining us. And I'll pass the microphone from here to Hrayr. He'll introduce himself and also the topic he's going to speak about.
Thanks, Arsene, for inviting me to present in this data fest. Let me share my screen and we'll start. No. I think I need to select the other desktop and then do this. You should be seeing now the first slide.
Yes, we see.
Yeah, thanks. So yeah, as Arsene said, I'm a PhD student at University of Southern California. Today I'll present our recent work that we published in this year's ICML. And it addresses a very important problem that I'm sure many of you who work with real-world datasets face constantly. This is the problem of learning in the presence of noisy labels. The work I'm going to present is joint work with my advisors and another student from my university, Hrayr. Okay, let's start in. So if you worked with real-world datasets collected in companies or provided by academia, such as ImageNet, you would notice that there are examples that are mislabeled, or there are examples that have dubious labels. For example, two labels might be applicable for one image, but only one of them is present in the dataset. Or an image can have a label attached to it, but when you look at that image, you don't see the relationship between the content and the label. So this arises in many settings. Here in this slide, I present a few cases where mislabeling arises. Crowdsourcing, including Amazon Mechanical Turk, is one of the major tools people use to collect datasets. In such datasets, usually one image is received by many persons to label, and when they label, you get label distribution per image. And some datasets do cleaning of that, meaning that they take the images that most of the labelers agreed, but some datasets just present you that label, like for example the majority label, and you would end up having datasets that have significant number of noisy examples. Another situation that is pretty popular is called distance supervision. Suppose you want to solve some problem, let's say sentiment analysis, but you don't have a very good direct data set of sentiment analysis. What you can do is take a few reviews and like scrap reviews from some websites and then look at the review number. If it's high, then say the sentiment is positive. If it's low, sentiment is negative. Obviously the data set, there can be high ratings with negative sentiment, and also can be the opposite case. So the data set you would end up having will be naturally mislabeled. Data augmentation usually can give us mislabeled examples. Suppose we have an image and then in the center we have a cat or dog. When we do random crops, we might end up having a crop that doesn't contain the object for which we have the label. And finally, there is this interesting case which doesn't arise often, but is pretty interesting. These randomized response experiments. This arises when we collect data set, but the collection is done with this randomized response strategy, meaning that we give a coin to the person and ask them to answer honestly if the coin flips, if coin shows heads, and answer randomly if coin shows tails. So this ensures that everyone knows that their true answer is not revealed, but at the same time we get a data set that majority of the labels are correct if everyone followed the rules. Okay, so I think that's significant introduction of the problem. This problem wouldn't be a challenge if neural networks somehow manage noisy labels, but it turns out that's not the case. usually when you have noise in the data set, these neural networks will memorize the noise, and as a fact that always leads to worse generalization. And another interesting property of neural networks is that they are pretty good at memorizing. At extreme cases, when you have data set with completely random labels, they will fit all those labels. So these two facts together kind of complicate the life when you want to train neural networks on noisy data. There are many approaches, heuristical and kind of more theoretical. This is no way kind of exhaustive list of approaches. You can find more detailed list in the paper, but I kind of highlighted the main directions. There's direction of designing loss functions, robust loss functions. This has roots in statistics, and there are few functions that are robust but might not train the network very well. Mean absolute error being one of them. It's recognized as a robust training loss. There are loss correction approaches where you try to find a confusion matrix for the labels and use that matrix to either correct the predictions, that's called the forward correction, or either kind of convert the existing labels back to the ground truth labels by applying that inverse confusion matrix. That's the loss correction approach. There's also lots of kind of heuristically derived methods when you want to detect what are the mislabeled examples. For example, you train for some number of epochs and then look which examples have the largest losses, and you name them mislabeled. So later you can do another iteration where those examples are not included or are included without label. Or you can, that's one approach. Another approach would be do some meta learning where one network tries to infer sample weights and the other one trains on the data set with that sample weight such that the performance is maximized on the validation data. There's this very interesting direction of co-training where you train two networks or three networks and they kind of teach each other, meaning that one can select examples for another, or you do the updates to their parameters whenever they agree, things like that. There's not enough time to go into details, and also it won't be very useful for this talk. So moving on, there are also the standard regularization techniques, which many of you will be familiar with, early stopping being the best and universally working one, dropout, weight decay. Soon we'll see that some of these are not very effective in battling with label noise. So what do we do here is kind of we take a general kind of perspective and try to understand what's that in our training algorithm that causes memorization of labels. And we come to the conclusion that whatever is memorized is stored in the weights, as I show here pictorially. The incorrect label 2 somehow gets somewhere in the weights, and our second part of our paper kind of tries to measure this memorized information and try to penalize it. To be able to do this penalties or measurements of information, we need a few information-theoretic quantities. I'll give kind of intuitive their definitions and a little bit intuition about them. If these quantities, I believe, will also arise in Hrayr talks, so it's useful to kind of get enough intuition here. The entropy of a random variable x just measures how random the variable is. It's constant, it evaluates to 0. If it's uniformly random, it's larger than that. So the formula for it is like this. If you don't know if you're not familiar with this concept, just ignore the formula and think that it measures uncertainty. Mutual information measures how much information one variable has about the other one, and is the difference in the entropy, in the uncertainty, after you know the second variable, as if we measure how much our uncertainty will decrease if we know variable y. That's the mutual information between x and y. And the KL divergence measures a distance, not distance as in real analysis, but like English distance between two distributions, and is given by this formula. Also, it's when p and q are equal, this will be 0. Otherwise, it's a positive number. Okay, that's enough for us. So let's start with the setup. We imagine we have n IID samples from unknown distribution, where here that data set is denoted by D. This bold X is a collection of n inputs, and the bold Y is collection of n outputs. And we assume here that there is some noise in labels, meaning the uncertainty of Y given X is greater than 0. There is some uncertainty in the Y even after we know the input X. So this can be for many things: label noise, or inputs being corrupted, or multiple labels being applicable for one X. Many cases are under this assumption. And let's say we have a classifier f, y, x parameters with W. So given parameters and X, it will give us distribution on Y. And then let's say we train this algorithm with this classifier with algorithm that is denoted by this condition distribution. It takes the data set and outputs probability distribution on weights. So this algorithm can be deterministic, evaluating to single W, or can be stochastic, such as HGD or Bayesian neural network. Doesn't matter at the moment. So given an algorithm, we usually formulate the loss as the cross-entropy on the training set. That's that standard log softmax loss everyone uses. So if we write it mathematically and take expectation over the data set, we would get to this formula. This measures how well do we do on the training set. Usually our algorithms we do, the most popular algorithm we do is so-called empirical risk minimization, meaning we want to find the best parameter value that minimizes the empirical cross entropy. And here's that algorithm denoted by AERM. Okay, the problem with this algorithm, it was described by Achille and Soato in their very good paper. I recommend everyone to check that out. You can decompose this quantity into 3 terms. The first one is the uncertainty that is present in the labels. This has nothing to do with our algorithm or classifier. Second one measures, this was unintended. Give me a second. Oh, tricky things happen. I need to go back. Okay, I think we were somewhere here. Yeah, the second term here denotes how good is our classifier approximating the true prediction distribution PYX. So this is the distance between P and F. And finally, we have this third term, which comes with negative sign, is the information in weights about labels that is not present in inputs. If we think a little bit about this, we'll notice that this is the amount of noise captured by weights, amount of label noise. And you can see, because of this negative sign, when we minimize empirical cross-entropy on the training set, we can actually do it well by just maximizing the last term instead of minimizing, let's say, the second term. That's why we can look at this objective and say, okay, then we found a nice regularization, right? We can just add this information term to that empirical cross-entropy, form this objective function, regularized loss function, and that would cancel this information part here, and we would end up having only the second term to minimize, which is pretty good. Unfortunately, that's very hard problem to solve, because here we would be minimizing over set of algorithms rather than set of parameters, right? We want to select the best algorithm. This is not the classical machine learning scenario. This is, if you want to know, kind of meta learning situation. Additionally, these quantities here, they look short and nice, but in reality, they are hard to approximate or work with. So the key contribution in this paper would be to kind of make this second term information term manageable and work so that we can work with. And yeah, so that would be the technical main component. I'll cover that, but let's see. Here I say it's hard objective. I already gave reasons why it's hard. Let's understand why it's excellent objective. So there must be some benefits of minimizing that information term. One of the benefits is that if we can ensure that information term is, let's say, epsilon very close to 0, then we can say that there should be this amount of guaranteed this amount of errors or mistakes done in the training set. For example, if we have 0 mutual information, we can put 0 here, and R here denotes the number of errors on the training set. It would evaluate that R is greater than, let's say, 60%. If we have 60% noise, meaning that if we capture no label noise information, this bound will say that then we have to do at least 60% error on the training set. Sounds trivial, but for non-zero values, it's not that easy. For example, if we capture 10 bits of information about label noise, how many mistakes we do on the training set. So that's the formula that denotes it. It's a lower bound on the number of mistakes. And if you think it's pretty strange thing that we are proving here, usually in machine learning, you upper bound number of errors on the test set. Here we are lower bounding number of errors on the training set. So here we are combating memorization on the training set. And this plot shows how this R will change as we sweep the mutual information term from 0 to larger values. Yeah, let's not concentrate too much on that. We might need some time. Another benefit, okay, we minimize memorization, but that's not significant because the algorithms that set W to 0 or do random things, they don't learn anything. They don't memorize, but they won't generalize too. And their training performance will be bad. So our next goal is to prove that minimizing mutual information term will also decrease some generalization bounds. So this one can write information weights have about the whole data set as information weights have about X, and information weights have about labels given X. So this is called chain rule of mutual information. And when you have label noise in the data set, this second term grows linearly with N. And if you use this generalization bound proved by Shu and Raginsky, you will get that this bound N here and the linear scaling in the mutual information term, they cancel each other, and this right term becomes constant, which is undesirable in machine learning. In machine learning, our goal of learning is to reduce generalization gap. Generalization gap, by the way, is the difference between train and test performance. I'm sorry not to tell from the beginning. Yeah, the goal in machine learning is to have a learning algorithm such that when we increase number of samples or experiences, it should have smaller and smaller generalization gap. So we see that whenever there's a label noise and the algorithm doesn't control this label noise information, then this bound will be meaningless. It won't go to 0 as N goes to infinity. Whereas if we successfully limit that term, then the whole situation depends how much information we capture about the inputs. That's another question. It's outside of this paper at the moment. Let's go ahead and try to see how something tricky happens when I touch with my mouse. It starts to go all the way back. Okay, here we are here. So we have this information term, label noise information. The key trick in this paper that was novelty is to relate information in weights to information in gradients. So in machine learning, when we train neural networks, we do sequence of gradient updates, and the final weights are just some aggregation of them. So you can apply the chain rule of mutual information to bound information in weights via this formula presented here. Next step is to upper bound mutual information by introducing some distribution Q phi. This is called variational upper bounding of mutual information. And here, the intuitive notion is the following. We are trying to predict the gradient at time t without using labels, only using the dataset inputs and the previous step gradients. So if we can predict the gradient without looking at the labels well, then that means the weights have no information about the label noise. Otherwise, we won't be able to do that. So that's why we have this upper bounding here. next step is when we predict gradients without labels, we actually use those gradients to train the classifier. So what we end up having is very simple. So if you lost me up to this point, now it's a good time to join. From now on, there will be no math. We have this main network, the classifier that we are trying to train, and there is this additional network Q, which tries to predict gradient at the iteration t without looking at labels. So what we do is we take this predicted gradients and use them to train the classifier. So we have two networks. One is predicting gradients of the other network. Final step that is needed to ensure the information term doesn't grow as we train or grow slowly is to add penalty to the predicted labels, L2 norm penalty, which means we usually want the predicted gradients to have small norm, not to grow large. And in the paper, there is explanation why that bounds information. Okay, so this, we can kind of summarize up to this point what we do. I described how to control this information term. We described that it's good. It'll have at least two benefits: reduced memorization, improved generalization. And let's see what's going on the left side on this plot. So here we have a simple data set, I believe MNIST, with 80% label noise, meaning 80% of labels are incorrect. And here we train 4 different networks. The first one we train is the standard classifier, let's say 4-layer convolutional neural networks without any special tricks. So if you see the training accuracy that goes to above 20% mark, number of correct labels, pretty quickly, meaning that after a few epochs, it memorizes the incorrect labels and at the end reaches almost 100% accuracy. And if you look at the test accuracy, where test set is a clean data set, you'll see that the test performance decreases as you start to memorize, as the network starts to memorize more. If we add dropout or weight decay, we combat the memorization a little bit, and because of that, the testing performance improves, but this is not satisfactory. And the red one here is the proposed approach, which we call limit. And here you see that it never passes significantly the 20% mark in the training data set. So it does 80% errors on the training set, but does well on the test set. So you see that the performance doesn't drop and goes to very high numbers. So we can conclude that the network avoids memorizing the label noise, which was our goal. Okay, let's go to a few more experiments kind of on not MNIST data sets. We have here CFAR 10 and 100. There is this label noise, uniform label noise, where you just decide that this example is going to have an incorrect label, and you flip a coin to decide which label it should get without looking at the image. So this is kind of a dumb label noise that doesn't arise in practice. It's just kind of synthetic situation we study in papers. Is the easiest label noise to combat, because let's say a plane might get by chance label cat. This won't happen. A plane might get sheep or something like that, but not cat in real data sets. The other noise actually respects the class relationship. So we have this asymmetric noise called pair noise. Birds can become airplanes, cat can become dog, deer become horse, and truck automobile, with some probability, of course. And we have this clothing 1 million dataset, which are ImageNet size images. And this is naturally collected dataset. The estimated amount of noise here is 40%. So we don't add any artificial noise here. We take the dataset as it is. So this large table here is one of those tables we see in deep learning papers, where the goal is to get bold on 1 row or 2 rows. Here I took a few baselines, so kind of one approach from one category. We have the standard training denoted by C, cross-entropy. We have the mean absolute error being MAE. This FW is the forward correction approach I described earlier. This DMI is recently introduced loss that tries to correct memorization and then kind of by trickily detecting the noisy labels actually. And this limit G and limit L are our approaches. The only difference is that distribution Q we were using to predict gradients. In one case it's Gaussian at the end, in another case it's Laplace distribution. And we can see that in many noise regimes, in many noise types, the approach does better than the other approaches, and sometimes they score pretty close. For example, on this clothing one and 1 million data set. This is not very interesting for our slides. Let's look at what other things you can do if you have this. So we can look at the gradient we would compute if we just do as PyTorch does. And let's look at also the predicted gradient and compute the distance between them, just Euclidean distance. So we are expecting that whenever predicting gradient is very different from the normal gradient, that means this example has noisy label. And if you just plot a histogram of that norm over examples, you would see that noisy, incorrect, and correct examples separate well. For example, in the easy cases where you have CFAR 10, 40% uniform noise, there is clear separation of this incorrect and correct examples. That's a very good sign. You can detect these examples, correct them, or remove them from the data set, or make them unlabeled. Look when it's CFAR 10, but with pair noise, a trickier noise, the separation is not that accurate, though the AUC score is pretty high, above 90. So still, if your goal is to improve the performance, you can do some filtering or other operations to kind of bootstrap the results. And finally, the CFAR 100, 40% uniform noise, I think is qualitatively similar to the first case. Not very interesting. They separate pretty well. Okay, also we can look to find what are the most mislabeled examples. It corresponds to looking what are these examples that score highest in this histogram plot. If you look at them, and here I plot one example per class in MNIST, you would see that even MNIST that was significantly cleaned and is considered one of the nicest data sets has challenging examples. For example, 8, this was labeled 8 but looks like 2. This was labeled 9, looks like 7. And this 5 is actually 3, things like this. Finally, there's another experiment I did recently. It's pretty funny. So there is this double descent phenomenon introduced recently where we take, let's say, CFAR 10 with some amount of labeled noise, and then we consider these ResNet networks and consider increasing the width of that network and measuring how the accuracy changes as we test accuracy changes as we increase the width of the network. So if you plot test error versus the width, you would see there is these two descents. This is against kind of the traditional bias variance trade-off perspective in machine learning, where you expect this test error to go down and then increase after one point where you get very complex methods or too much capacity. This is not the case, and I was looking at this plot and noticing that this kind of the double descent phenomenon is visible much more when you have noisy examples. So I was thinking this might be just denoting that something is very related to memorization, as if double descent is directly related to memorization. So I tried to apply the proposed method on this setting, and the results are pretty interesting. So the blue one is my reproduced results for CFAR 10 with 20% label noise. You can see that there is some double descent. And if you do early stopping, in the actual paper, they don't do early stopping. If you do early stopping, you can eliminate the descent. And you can see that the numbers improve as we increase the network weight. So this is why over-parameterization helps. This is now the current consensus that larger networks perform better. And when you, when you apply the proposed network, you see that with early stopping or without, there's not much difference. And what's more interesting, that the gap between cross-entropy approach with early stopping and our proposed approach grows as you increase K. So as we increase the network, this approach we propose gives more kind of improvement, which is pretty nice. I think we need to understand why this happens a little bit more. So that's what I plan to present today. Thanks. Please check out the paper if you are interested. The code is also available.
Thanks a lot, right? We already a bit behind the schedule, like a couple of minutes. So if you have questions, I'd encourage you people to ask the questions in the Slack channel too, right? But to be honest, I can't resist to ask one question, and please answer it only in case if you have a short answer. As a practitioner, is there like one term that I can add to my cross-entropy loss in PyTorch for all this that you presented to be able to use?
You will be able, it's just not one term. You need to kind of copy the network you have, get the second network. Actually, if you go to the directory, there almost everything is coded there. So you have this module, it wraps another network. So you give a network to it, and it makes this two network setup out of it, where one tries to predict the gradient for another one. It's not as convenient as, let's say, adding dropout, but pretty doable. That's
okay.
what I want to say.
Okay. Thanks a lot, Ed.
Thank you.
Our next speaker is Hrayr Hrayr. He is the director of Yerevan, and I think he'll take off from here.
Thank you, Arsen, and thank you, Hrayr, for the nice presentation and providing the required notation for my slides.